All right. Hello, everyone. I'm Bernd, and today is day 9 of Advent of Code. So, today's puzzle was about a rope, and in particular, our rope consists of a head and a tail, and they must always be touching. So, the tail must be either in the 8 fields around the head or at the same position of the head itself. And then, throughout the puzzle, the head will move around, and the tail will follow it. And we will be supposed to keep track of which position the tail will go to. So, for example, if the head were to go right, then the tail will follow it in order to stay in these positions around the head. Similarly, if the head goes up, then the tail will, in this case, and the tail is like diagonal one away, the tail will follow it and it will do so diagonally in order to be as close as possible to the head. And yeah, so we have a list, we give him a list of moves for the head, and the tail will follow it all the time. So we also give him an example. If they start here, the head and the tail, then whenever the head moves right, the tail will follow it. And then from this position, if the head moves up, the tail will stay here because it's still in the 8 positions around the head, so it doesn't need to move. And then if the head moves one more up, then the tail will need to move with it, and it will do so diagonally to minimize the distance between the head and the tail. Okay, and that's already the puzzle. How can we solve it? So of course we first need to read the lines, so we need to read the file and split it into lines. And then we'll define a vector class. I guess we could also have used something like NumPy, but I didn't wrote it myself this time. So what is a vector? We will initialize it with a x and a y coordinate and save those. And then we'll perform different methods to do, for example, addition of two vectors. So if you want to add two vectors together, we will have to define this add method. And then the new vector just should be the vector that has the first two components added, and also the y component of the vector itself, and the other vector should be added. Similarly, we can define subtract, and if we want to compare vectors, we also want to define the equal function, or the method. So two vectors are equal if both the x coordinate and the y coordinate are equal. And then we also, in order to put it into sets or so, we also want to define a hash function. So there we just use the same hash function as the tuple of x and y. So we don't need to think about it much. We also define two properties that might be useful. So in particular, the maximum norm is just we take for each part for the x and y component, we take the absolute value, and then we take the maximum value of those two values. And we'll also define the L2 norm squared, or the Euclidean norm squared, which is just square the x value and add the y value squared. Okay, so in our input, we have a few directions. That's like right, left, up, and down. We define a dictionary, and we assign to each direction the corresponding vector that would represent that direction. And yeah, then we can process the line and get the moves of the head. So we first start with a list of moves, probably a list of vectors, and it starts empty, and then we go through all the lines. And the line could, for example, be like this. So the first part is giving us the direction, and the second part is telling us the amount of steps done in this direction. So for the direction, we take the corresponding move, which is given by the dictionary, and will be a vector, and then we just append the move to the moves, and that's done that many times, like as many times as given by this string for the second part. Okay, so that way we can like read the moves of the head from the file. Then we need to consider the moves of the tail. So there's 8 different steps that tail can do. So in a grid, the tail goes either one step to the right or diagonally, or one step up or diagonally, or one step to the left or diagonally or so. So in particular, the x coordinate of this vector corresponding to the step can be in like +1, 0 or -1. The y coordinate can also be in +1, 0 or -1, but we exclude the 0 vector because that's not really a step. So that's given by this. And then maybe the main code would be this chase function. So there's like where the tail chases ahead, both vectors, and I'll output the new position of the tail. So first we'll consider the difference between the head and the tail, and then if the tail is, this is the position of the tail, if the head is in those 8 positions around it, or at the same position actually, the tail will not move at all. So we can do this by the first part. So these 9 positions are given by the max norm. So if the difference has max norm at most 1, the tail will not move at all, and we can just return the tail value. Otherwise, if the head is on those outer positions, so for example, if it's here, the tail will move 1 step closer to the right as well. If it's one of those 3, the tail will move diagonally. And in particular, the tail will almost move in a way to minimize the distance between tail and head. So instead of writing a complicated code, that helps us a lot to simplify the code we need to write. Noticing this. So yeah, otherwise, if the we had the case that the max norm is smaller at most 1, which corresponds to the tail being in, or the head being in those 9 positions. Otherwise, we get the best step, or this get best step function that gets us the step that gets us closest to the goal position. So how do we do that? We just initialize the best L2 norm squared seen so far as a high value, and then we go through all possible tail steps. For each of those, we take the difference of the goal position and the step, and then take the L2 norm squared of this vector. And then we just find the best one by comparing the current L2 norm with the best L2 norm we've seen so far. If it's smaller, then that's a better step. So we update the best step, and we also update the best L2 norm seen so far, and return the step. So with that, now we can get the step that gets the tail closest to the head, which is what happens according to our puzzle. And then we just return the new position of the tail, which will be the old position of the tail, plus the best step. So with this code, we can solve our problem. So yes, this solve function, which just starts the head with the head position at 0, the tail position also at 0. We'll also keep track of all the points the tail visited. So for this, we define a set of the tail positions will be a set of vectors. And because we defined the equal and the hash function, this will make sure that no vector will be in there twice. So this will already get rid of duplicates for us. And at the beginning, it will be just the starting position of the tail. Okay, then we process the lines and get all the head moves, all the moves that the head will do. And then for each move of the head, we first update the position of the head. And then we update the tail position by applying this chase function to the head position and the old tail position. And then we also add this to the set of tail positions because we want to keep track of it. And then the number of different positions the tail visited will just be the length of this set. Okay, so yeah, that code hopefully works. We have a little test input given, and we also know that in this test input the tail will visit 13 positions. So let's run it, and that looks promising. So we can also run the code on the proper input, and the result also works out. For part 2, we can reuse a lot of functionality from part 1. So particularly we can use vector and get head moves and also the chase function. And part 2 is about a rope that's not only 2 pieces long, the head and the tail, but this time it's in total 10 pieces long. So we have the head and then 9 tail pieces. And then we want to keep track again of the last part of the rope where it goes. So for this, we can define a rope which will consist of 10 vectors. So the first one is the head and then 9 tail positions or tail parts. And again, we want to keep track of the tail positions, would be a set of vectors, and this will be the positions the last part of the rope visited, so the rope at index 9. Again, we'd get all the moves the head will do, and then for each move, we first update the position of the head. So the head is the rope at index 0, and we add the head move. And then for each other part of the rope, so for index for I in 1 to 9, we will update the position of the rope by applying this chase function to the position of the part before and the current part. And yeah, that will update iteratively each part of the rope, and then we want to keep the position of the last part of the rope, so we added the tail positions, and again we return the length of the tail positions, which will give us the unique, the number of unique positions the tail visited. Okay, we give them a second test input for that, so we use both of them to test our code. For one, the solution, the tail visits one position only, for that one 36. Let's run it, and that looks promising as well. And also, if you run it on the real input, it seems to work. So that's great. Yeah, that's already it for today. I hope you enjoyed today's puzzle. Best of luck for the future, and see you around.